Hi, welcome. In this video, we're going to go over CPU scheduling. So let's get started. All right, so first we want to talk about different types of processes. So what we mean by different types of processes is that you have I/O bound processes and you have CPU bound processes. So what does that mean? It means that I/O bound processes are those that spend more time doing I/O and less time on the CPU, and CPU bound processes are those processes that spend more time on the CPU. So your operating system wants to get a good mix of this, because if you don't want to have the CPU sitting there idle while all of the processes are waiting for events, and you don't want to have all the processes waiting for events and never get any time on the CPU. So this is a big factor in doing CPU scheduling. The next thing we want to remind you about is a context switch. So a context switch is overhead. What does that mean? It means that the operating system needs to use the resources of your computer system in order to do the work. And what is a context switch? It's saving the current state of the process that's currently executing and loading the context or the data for the next process. Obviously, if you start executing a process and then it gets switched, you don't want to have to restart it every single time. So the operating system needs to get involved and save the context and load the context of the next one. This is overhead. Again, remember that the operating system is a manager that needs to use the resources that it's managing in order to perform its tasks. So while the operating system is doing this, it is taking away from the tasks that are getting done. So a lot of times you might think, oh, it's very good to switch, things very quickly, but when you're switching things very quickly back and forth, then you end up doing a lot of overhead, a lot of context switching, which could impact performance. The next thing is system schedulers. So just to remind you, we have a long-term scheduler, we have a medium-term scheduler, and we have a short-term scheduler. The long-term scheduler is in charge of admitting processes into the system. You have to, in order to take a program and turn it into a process and admit it into the system, it needs to be loaded into memory. This scheduler, this unit of your operating system, not all operating systems have them, but it is in charge of admitting new processes into the system, and maybe there needs to be an order in which they get admitted into the system. Some operating systems have what's called a medium-term scheduler. In other words, it's called a swapper. So sometimes there are processes that have been inactive or are just taking up space in memory, and the operating system may swap those out for other processes that get admitted. Not all operating systems have a medium-term scheduler, but all systems, even if they go first come, first serve, have a CPU scheduler. So in this unit, we're going to talk about different CPU scheduler algorithms, how to evaluate them, how to do calculations to compare them. So let's get started. So the calculations we will be doing, so we're going to be focusing on the CPU scheduler, and the calculations we're going to be doing. You have throughput. Throughput is the amount of work that gets done in a certain amount of time, or meaning the amount of processes or the amount of the amount of processes that get completed within a given amount of time. So obviously you have to take a snapshot of an amount of time and say, okay, in this amount of time we've had this much work done, and that's how you would measure throughput and compare it between different types of CPU scheduling algorithms. The next calculation is going to be CPU utilization. These two things you want to maximize. You want to maximize your throughput because you want to get a lot of jobs done in a certain amount of time, and CPU utilization means the percent of time that the CPU is active. So what does that mean? It means, so if you have here's your CPU, say we'll just represent this as a CPU, and time, this is 100 time units to be simple, and the CPU is active from 0 to 20 and is doing nothing for all this 20 to 100. It's just sitting there idle. This is not good CPU utilization because this would only be a 20% CPU utilization. So you want to mix your different types of processes. If some are in I/O, then you want to put other ones onto the CPU. Sometimes it might be idle, for a little, maybe it's idle for 10 time units here, but then it picks back up and starts to work again, and then is idle again here for this. So here where the CPU would be busy for 20 time units, idle for 10, busy for another 60. So that would be now a 70%. Is that correct? No, it would be an 80% CPU utilization. 20 here plus 60 here is 80% CPU utilization. Other calculations we're going to do, these are to evaluate and compare different algorithms. We have response time. That's a one-time measure from when the process gets admitted. It goes from admit to the first time on the CPU. It's a one-time measure, right? So your processes get admitted into the system, and if there's something else on the CPU, they're going to have to wait, right? So response time is a one-time measure from the time when it gets admitted into the system until the first time it gets on the CPU. Then you have wait time, and this is the sum of the time spent in the ready queue. So response time is response time would be the first measure of wait time, right? So you get admitted into the system, you wait in the ready queue, you finally get on the CPU, that's your response time. Then something happens, you get interrupted, or you go to an event, or you go back into the ready queue, then you're going to add all of the times that you're sitting in the ready queue. That is a sum, that is your wait time. And then our last calculation is turnaround time. Turnaround time is the total time from admit until exit. So that's the sum of the periods. So turnaround, you would add up your waiting time. Keep in mind that the very first waiting time is your response time. So you would add up your waiting time plus all the time on the CPU plus all the time that you're in I/O or at an event, and that is going to equal your turnaround time. So you add up all the time that you're active. So it's from the time you get admitted into the system until the time you leave the system. And we're going to be using these charts similar to this called Gantt charts to practice CPU scheduling algorithms by hand and do comparisons. And what are some of the CPU scheduling algorithms? Well, there are two types of CPU scheduling algorithms. There are non-preemptive algorithms, and there are preemptive algorithms. A non-preemptive algorithm is one in which as soon as a process gets on the CPU, it continues with its current burst on the CPU and does not relinquish the CPU until it has completed its current burst. Some non-preemptive algorithms could be first come, first serve, shortest job first, or priority. Then we're going to go over some preemptive algorithms. Some preemptive algorithms include round robin, shortest remaining time, and preemptive priority. So these are the first algorithms we're going to study and do some exercises with. And there are a lot of other algorithms out there where they're always coming up with new ideas for different types of algorithms, but these are basic CPU scheduling algorithms that give you a good sense of how they work and how you can compare how these different algorithms work with different types of processes. All right, so we have our process types. Now this is everything that I just said, but repeated and neater. So if you're taking notes, you can now read what it says. That was just overview, and now I will go one by one through each of these topics that I just talked about. You have two types of processes. You have I/O bound processes. Those are the processes that spend more time in I/O. And you have CPU bound processes. These are processes that have longer CPU bursts. I/O bound processes have shorter CPU bursts. Now this is important to note because you don't want to have your CPU sitting idle. You want to maximize your CPU utilization, and you don't want to have I/O bound processes never get any time on the CPU. So that's why you use different techniques to try to get a good mix and utilize the resources the best way. So remember that a context switch is overhead. That means that the operating system needs to use the resources of the computer in order to perform a context switch. What is a context switch? Saving the state of the current process and loading the state of the next process. Now don't be confused by the word state. I know that the state of the process is one part of a process, but this means the entire state or the entire context, the PCB, everything about what is happening with the process, not just what state it's in. So this word state doesn't stand just for the state it's in, like new, ready. It also stands for the word state can also just stand for the context or all of the information about the current process. Schedulers. We have our long-term or job scheduler. This one decides which ones get admitted into the system and brought into the ready queue. We have our short-term or CPU scheduler, and that is the focus of this module. We will be talking about different CPU scheduling algorithms, preemptive and non-preemptive algorithms, and we'll be doing some exercises with some different process data to compare the different algorithms. Some have a medium-term scheduler. This is to take those that are in memory if there's not enough space and move them out of memory into the disk and bring some other process in. That's called swapping or medium-term scheduling. All right, so we have our short-term scheduler, which is our CPU scheduler. It's going to select from those processes that are in the ready queue which one is going to get next on the CPU. So you have your processes. So this CPU scheduler has to work very often. You have your processes that are ready and waiting in the ready queue. And then you have your dispatcher, which is going to dispatch whichever process that's in the front of the ready queue onto the CPU. So that process that was in the front of the ready queue, using some type of algorithm, maybe first come, first serve, or some priority-based algorithm, for example, one of those processes is going to be in the front and it's going to get dispatched onto the CPU. And then you're going to have a whole list of processes still in the ready queue waiting. So you have a bunch of processes that are in the ready queue waiting. So this could represent our processes that are in the ready queue waiting. And when it's this one's turn, it gets dispatched and it will be on the processor. So say that's first come, first serve, or however these are queued up. Now, this one is running and lots of things can happen. It could be interrupted. So this one could get interrupted, and then the CPU scheduling algorithm, once that one gets interrupted, then it's going to have to decide from those that are currently in the ready queue which one goes next. Other things that could happen, a new process could get admitted. So you have these processes are in here, you got one on the ready queue, and this one gets admitted. The CPU scheduler is going to need to decide where in the queue this new one is going to go. Sometimes you have processes that get swapped out. So Maybe you need, some of them have been sitting here for too long, so we're going to take this one out and swap it out because we need to admit a new one in and we don't have the space. And then when that new one gets admitted, you're going to have to decide what order it's into. Also, you have processes that go out for events. So you have a process out here that was out in an event and it comes back into the ready queue. So now your CPU scheduler is working again to decide where this one that just came in from an event is going to go in the ready queue. So this CPU scheduler is working all the time. You have processes getting admitted into the system, processes that are getting interrupt, processes that are coming from events, processes that are getting swapped in and out. So the CPU scheduler is always working, and it may be using a simple algorithm or it may be using a combination algorithm. There are a lot of different algorithms out there trying to give the most work the best for the particular types of tasks that run on that computer system. The dispatcher. The dispatcher is just the module that takes by this short-term scheduler. Another word is called the CPU scheduler. And the dispatcher is just going to decide which one goes next, but a context switch needs to happen. Every single time that you're switching from one task to another on the CPU, you need to save the program counter, all of the data, all of the information about the current process, and load the context of the one that's getting put on the CPU. You have to obviously jump to the proper location to start. That's why you have the program counter. You don't want to reset all the processes every time they go to execute. And so there's some more time in addition to context switching, in addition to the operating system using resources for the context switching overhead, there is a dispatch latency, and that is obviously some time that it's going to take to switch from one process to another. So it might seem like it's a really good idea to switch things very quickly and use like a round robin with a small time quantum, but that involves a lot of context switching. So let's talk now about CPU scheduling algorithms and the calculations that can be made to compare the different algorithms. The first one, well, first we want to recognize that a CPU burst just means the time that a process is on the CPU. So if we have a chart like this, and this represents the CPU starts at time 0, each process is going to get a little bit of time on the CPU. So say process 1 comes in and gets 10 time units on the CPU. That would be the current CPU burst for process 1. And then say process 2 comes in and gets 15 time units on the CPU. So that's going to be the CPU burst for process 2. So we're going to be using, this is called a Gantt chart, to draw this, and the Gantt chart is going to represent the CPU. So as we're practicing different algorithms, we will be using Gantt charts to do it by hand and practice and get some results and see how different algorithms work with different types of processes and different amounts of CPU bursts. And then we're going to start out with CPU bursts, and then later we're going to add I/O time into our exercises. But first, we're just going to start with CPU bursts. So CPU utilization, we've already talked about that. That's the percent of time that the CPU is busy. So say here, our total time here is, say we have another process 3, that goes until time 50, and our total time is 100. I know that's not to scale, but that's okay. And the CPU is not working here. That would be 50% CPU utilization because the CPU was busy for 50% of the time, and 50% of the time it was not doing anything. So that would not be, you want to maximize your CPU utilization. Throughput is the number of processes that are completed in a given amount of time. So obviously when we're doing these exercises, we're picking, a time frame snapshot to do these comparisons. Turnaround time. So turnaround time is the sum of periods spent in the ready queue, waiting for the CPU, possibly in I/O, and on the CPU. So a process comes in, a process gets admitted, it's ready. This is going to accumulate wait time. The first time that it waits is going to be called its response time. The first time, this is a one time from the time admit to the first time on the CPU. Okay, so turnaround time, the process gets admitted into the system and it's in ready and it needs to get onto the CPU, but it has to wait. So while it's waiting until the first time it gets here, there's going to be a response time. That's the amount of time it waited for the first time to get on the CPU. Then it gets on the CPU and then it interrupts and then it goes around. And so waiting time is the sum of periods in the ready state. Turnaround time is the sum of periods doing everything. Waiting. So waiting and in the ready queue, that's the same thing. Out in I/O and on the CPU. So the process is either going to be doing one of three things. It could also be swapped, but in our exercises, we won't be adding the swapping part. We will just say out I/O or event, meaning it's not waiting for the CPU because it's not ready to be on the CPU. So a process is either going to be ready and waiting for the CPU, on the CPU, or out in some type of I/O or event. So here again is a reminder of the process states. Processes, so any process that is right here, that is where they're accumulating waiting time. If they're out here blocked or they're over here swapped or doing something else, any kind of event, then they are accumulating I/O time. So again, for our exercises, our processes are either going to have wait time, that means they're ready, CPU time, that means they're actually on the CPU, or I/O time, that means they are at some type of an event. So if you add these up, then that is going to equal their turnaround time. And the very first time they get admitted from the admit, they get in the ready queue and they wait for the very first time, one time measure, that's going to be their response time, which makes sense. It's the response, right? So if process X gets admitted into the system and the CPU is busy doing something else, it's going to get admitted and it's going to sit here and it's going to wait until it finally gets its first time on the CPU, and that's going to be its response time. So let's erase all this because I have it nice and neat. So that's the response time. It's the one-time measurement from it very first gets admitted into the system until the first time on the CPU. Then the wait time is going to be the sum of the time spent in the ready state, ready to get on the CPU. Just after it goes to an event or gets interrupted, it's just going to add up all the time that it's waiting. And turnaround time is from when it gets admitted until it exits. So turnaround time is the sum of the wait time plus the CPU time plus the I/O or event time. So here are an overview of the different CPU scheduling algorithms. So we have non-preemptive algorithms. A non-preemptive algorithm just means that once the process is on the CPU, it will not relinquish the CPU until the current CPU burst has completed. So it's not going to get interrupted. If it has a CPU burst of 20 time units, it's going to stay on the CPU for the full 20 time units until it's done its task. And then obviously processes don't just get admitted, do one thing on the CPU and exit. This is the current time that it's on the CPU before it needs to do some type of an event. The different non-preemptive algorithms is first come, first serve. That means that processes get the CPU in the order in which they arrive. Shortest job first means that those processes that have the shorter CPU times get to go first. One thing you need to note is that processes do not have a thing in their context that indicates how long their CPU burst. So a process doesn't get admitted into the system and automatically, oh, I'm in the system, my CPU burst is 5 time units. But there are processes that tend to have shorter CPU bursts, so maybe they could be given a higher priority, or there are some calculations that can be done to try to estimate and predict what their CPU bursts are going to be. But both shortest job first and priority are priority based, right? A priority algorithm could just be that a process is assigned a priority. Shortest job first, the priority is based on the length of the CPU burst. Preemptive algorithms mean that a process can be kicked off the CPU, maybe for a higher priority or maybe for a time quantum. The different algorithms that are preemptive are round robin. That is first come, first serve with a time quantum. Shortest remaining time. So sometimes a process can get kicked off, but then you only keep track of the remaining time, right? Why would you need to keep track of the part of the burst that it already had completed? And preemptive priority, a higher priority process will kick lower priority processes off of the CPU. This could also apply to threads, but since we're just started on processes and this is just about CPU scheduling, we can use the word task or just say process because we're just evaluating these algorithms. Starvation can happen in any type of priority-based algorithm: shortest job first, shortest remaining time, priority, preemptive priority. And all this means is lower priority tasks or lower priority processes could starve for CPU time. And that would make sense if you have a bunch of high priority processes coming in. The low priority processes are going to keep getting moved to the back, and the higher ones are going to keep moving to the front, and it's going to push all of those lower priority to the back, and they will starve for CPU time. So there are techniques. One technique is a technique called aging, and you could raise the priority of lower priority processes over time. After it sits there for a given amount of time, you just raise the priority. This is a technique to avoid one technique that could be used to avoid starvation. Okay, so these are the calculation again: CPU utilization, turnaround time, waiting time, and response time. So we're going to do some algorithms. In the next video, we're going to get started doing some algorithms. This is just reviewing what the wait time is and what the response time and the turnaround time is. And in the next video, we will start with some non-preemptive algorithms: first come, first serve, and shortest job first. And then we will move on to priority-based algorithm, preemptive, round robin, preemptive priority. And finally, we will get to some combination algorithms, multi-level queue and multi-level feedback queue.